So no.
Okay, I got it. I appreciate that.
Okay. Here's our molecule for the day. It's Valium. I think everybody knows at least a little bit about this particular substance, even if you don't have personal experience with it, mainly for anxiety, I don't know, for your grandma or something that she has a stash of in her medicine cabinet. Um, and it's got, I think, kind of an interesting structure. It's got some rings, it has nitrogen and oxygen, and it's got a chlorine. We'll come back to it in a little bit. We're going to do some drawing practice with it, but that is our molecule of the day. So last time we talked about starting to draw, we drew some condensed structures and we sort of started to draw skeletal structures, but I want to talk a little bit more about specifically what we include in a skeletal structure and what we don't include. So, I mean, well, we can kind of just look at it and see, but let's make a list of all of the things, at least in skeletal structure, what we include and what we don't include. So we are going to include bond lines. So even if we don't draw every single atom, we are going to draw every single bond. So we've got, there we go, there's a single bond between a carbon and a nitrogen. We've got, this is a double bond between two different carbons, and so on and so forth. So we do include bond lines. We always draw heteroatoms. So heteroatoms are anything other than carbon or hydrogen. I don't think anybody has ever called carbon and hydrogen homoatoms, but you get the idea. Anything that's not a carbon or a hydrogen is a heteroatom, and all heteroatoms always have to be drawn in skeletal structures. So we have four of them here, one oxygen, two nitrogens, and a chlorine. These heteroatoms also tend to be quite interesting in terms of their reactivity, more so maybe than the carbon atoms, subject to debate. And so drawing them out helps us see those really clearly. We're also going to draw all hydrogens. On heteroatoms. There's not a good example here because none of these heteroatoms have hydrogens on them. So what's something that people tend to combine with Valium? Well, maybe this substance, ethanol. Don't do this, by the way, but I imagine somebody has done this before. So that's the structure of ethanol, and we've got two carbons there and there. We have a heteroatom, the oxygen, and importantly for this part that I'm discussing is we have to draw the hydrogen on that oxygen. So let's see. I don't like my red colors, but it's all right. So that is incorrect because we have to have a hydrogen on that oxygen to give it, well, a full octet and its valency of 2. Okay, the last thing that we must include always on skeletal structures is formal charges. So this molecule Valium does not have any formal charges on it, but if it did, we would absolutely 100% like have to include those. And that just doesn't just go for skeletal structures, that goes for condensed. Literally any time you draw a molecule, you have to write formal charges or else it's wrong. Okay, things we're going to omit. We already talked about this, but we're not going to draw the carbons explicitly. Of course, we can still see where they are because they're at each endpoint of a line. In that particular case, there's only one carbon in the structure of Valium that's at the endpoint of a line, and that's up here at the top. All the other carbons are at vertices of lines. So the ones that might be a bit, I don't know about difficult to see, but there's a carbon right there at the base of the oxygen, if you like. There's one there. That's a vertex, even though the angle is pretty shallow, but sometimes with these large rings, you have to draw them like that. And everywhere else that there's an intersection is a carbon. Other things we omit are hydrogens on carbons usually. You're always free to draw the hydrogens out on carbons, and in fact, we're going to do that in many cases because that helps us with bookkeeping. And also, we're often going to omit lone pairs. Again, it can be very helpful to draw out lone pairs explicitly. But as you can see on our structure of well, actually, let me do that now. On our structure of Valium, all four of our heteroatoms have some sort of lone pair activity going on, but they haven't been drawn here. And that's fine. If I wanted to add them, this oxygen gets 2 lone pairs. The nitrogens each get 1 lone pair. And the chlorine gets 3 lone pairs. If you're still wrapping your brain around how many lone pairs each atom gets and what particular configuration, that's okay. Just make sure you refer to that cheat sheet for the formal charges. It's really a cheat sheet for formal charges and lone pairs. And that'll show you the number of lone pairs that each of the various elements, at least that we're going to use, have on them under various conditions. So we can actually sort of split this into a couple rules that we can follow. And maybe this will be a bit of review, but it's not bad to go over it again. So each corner or each endpoint of a line is a carbon atom. So there's in hexane, and that's a carbon, 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 and that's a carbon. This is not standard notation to write the little C like that, but just for illustration purposes. And straight chains of carbon atoms, which I would consider this to be a straight chain, even though it doesn't look straight, are drawn as zigzags. We'll continue with our hexane example because it's easier than Valium. Hydrogens are usually emitted. Sorry. So there's the structure of hexane with no hydrogens, but we can draw them all out. And in fact, I'm going to draw them all out without drawing the carbons. So we're kind of just gonna draw the Lewis structure, but without the carbons. So the way you should go about that probably is just redraw the skeletal structure. Just make sure it's sort of big enough because you're gonna have to fit all the hydrogens in there. And then the carbons on the end are gonna get how many hydrogens? 3. Carbon has to have 4 bonds. And all 4 carbons in the middle are going to have how many? 2.
Sorry, can you explain how you got the 3 and the 2?
Yes. So actually, let me label these carbons back on the first one. So the blue carbons at the end, there's only one bond that's been explicitly drawn to this blue carbon. And these bonds here are all carbon-carbon bonds because each of these dots is a carbon atom. And so for carbon to be neutral, it's got to have 4 bonds. And so if we know that one of the bonds is to another carbon, by process of elimination, the other 3 have to be to hydrogen. Same goes for the hydrogens in the middle, the yellow ones. For each of these 4 carbons, there's 2 bonds explicitly drawn. That means we have 2 bonds to carbon, or it could be it could be an oxygen or something, but in this case, 2 bonds to carbon atoms. And so by process of elimination, it's got to have 2 other bonds, and those have to be to hydrogen. So neutral carbon, we call it tetravalent, tetra 4. So it makes 4 bonds. So go ahead and start practicing that kind of thing because this is going to get really important really fast. Note being able to look at a structure and see where the hydrogens are. And the one and only way to do that is to look at the number of bonds that each carbon already has to it that have been explicitly stated in the skeletal structure and fill in the rest with hydrogen to give it a total of 4 bonds.
Supposing we automatically assume this hydrogens in coverage?
Yes, unless we could have a skeletal structure that looks like that. That's a complete skeletal structure. We've got, going to keep the color scheme going here. We've got 4 terminal carbons. Each of those blue carbons have 3 hydrogens because each of them has 1 bond drawn to it. So the other 3 bonds to make 4 have to be hydrogen. But in this case, we have a vertex here in the middle. Come on. A vertex here in the middle in pink that has 4 bonds to it. So a carbon with 4 bonds to other carbons, how many hydrogens does it have? None. Replace pink with your color.
Something else, it's bonded to hydrogen.
Correct. Yeah. That is the assumption, unless you're told otherwise in the chemical structure. Okay, so those two rules that kind of goes with the includes and omits list that we talked about. There are some, I say some, there's like a bunch more rules, but there's some other rules that are well, I guess they're less concrete. So next rule has to do sort of with Vesper theory, and that is to keep bonds as far away from each other as you can. Valence shell, electron pair repulsion. Bonds want to be as far away from each other as possible. And so let's say we have the skeletal structure of acetone, which looks like that. First, we can actually continue with our exercise that we've been doing, and that is to look at those two carbons that are endpoints, and we have another carbon, which you got to be careful not to miss. This one is missable. I mean, now that I've pointed it out, it doesn't look missable, but trust me. So here, the blue carbons are at the end of a line, and so they have 3 hydrogens. The pink hydrogen has 4 bonds, 3 bonding domains, because there's only 3 things attached to it, but it's got 4 bonds because of that double bond. And so how many hydrogens does that pink carbon have? 0. Not 1, 0. Okay, anyway, what I was saying with this rule, keep bonds far apart. Okay, so in this case, it's easy. I've drawn things in a triangle, but at some point you may be tempted based on the way things are, maybe you're crunched up against the end of the paper or something, to do this, which isn't wrong. But he looks uncomfortable doing a split hanging upside down, right? So those 3 things that are attached to the carbon are not as far away from each other as you can possibly get. But for example, you could draw that. That's fine. That's okay. Another thing that this sort of leads into is this molecule is identical to this molecule. Just because I've drawn it upside down, that didn't mean anything. All the connectivity is the same and the bonds are the same. Technically, the one in the middle is correct, but ugly. So don't draw it like that, please. Okay, rule 4. For single bonds, direction is irrelevant. So what do I mean by direction? So if I forgot this structure, which has actually 3 different kinds of carbons. We've got these terminal carbons at the end, which have how many hydrogens? This one has 2. What about this one? 1. If you can count to 4, you can do organic chemistry. Okay. So this structure is exactly the same, 100% identical to this. So all I've done here is take these N carbons on the left and the right, and I've just bent them down. So if you do that exercise again, okay, these still have 3 hydrogens on them. These carbons, sorry, you can't see my white pen on the thing, but these carbons here still have two hydrogens on them. The direction you draw the lines doesn't matter. So you could also, if you like symmetry, maybe this will bug you a little bit, but you could draw it like that too. And that's correct. Once we get into naming of these molecules, that will give you an additional bit of assistance in seeing that these are all the same, because if you go through these, thank you, clouds. If you go through these and do the systematic naming convention, you're going to get the same thing for each. And then you'll say, oh, okay, yep, these are the same because of reasons that we'll get to in a moment. Okay. Rule 5 of 7, by the way, we're almost done. Rule 5, we already talked about, so this is review. Heteroatoms, so those are non-carbon and hydrogen atoms, nitrogen, oxygen, sulfur, halogens. And any hydrogens that they have, which could be 0, but sometimes they do have hydrogens, must be drawn. I don't know if that's actually English. Must be drawn explicitly. Always and forever, you have to draw them out. So generally, I think the heteroatom part is easy because how are we going to know that there's an oxygen there if you don't draw the oxygen? But you might say, okay, well, if I don't draw hydrogens on carbons, then I don't have to draw them on heteroatoms either. Wrong. Soon enough, you should feel very uncomfortable with the structure on the right because there's an oxygen atom hanging there. It doesn't have a formal charge. Again, that we'll get to that in a moment, but it doesn't have a formal charge and it doesn't have a hydrogen on it. So it's very unhappy. So that's not okay. Additionally, if you have something like this, there's a nitrogen atom with 3 CH3 groups attached to it. Again, if you draw this and you're trying to tell me, oh, there's a nitrogen in them, well, no. No, those are completely different molecules. Okay. Hopefully that should be kind of obvious, but I feel like it would embarrass me to tell you how many times I've just drawn a structure and like missed. It's always a nitrogen for some reason, and just miss a nitrogen. And then you have to go in and you're like, oh crap, there's a nitrogen in there. You just draw it on top. I will do that as well from time to time. Whatever. Okay. Rule 6. This is the one that probably will send some of you to organic chemistry jail, and that is never, ever, ever in a million years give a carbon more than 4 bonds. Sounds easy, but it's also an easy mistake to make. Oh, pains me to draw some of these things, but that is wrong. I think we can see the problem, which is here in the middle. This carbon has 1, 2, 3 bonds to CH3 groups, and then it's got this double bond. So that's a total of 5 bonds. That is illegal. It's always 5 bonds. If you manage 6 bonds, I reserve the right to laugh at you, but There's another one. Here we have a ring, a six-membered ring. Get used to drawing those hexagons, by the way. This carbon here is the culprit. We've got two bonds to this ring system. And then we've got three bonds to CH3 groups, total of 5. That is illegal. If it looks like a star to you, that's why these are sometimes called Texas carbons. So don't draw a Texas carbon that has 5 bonds, looks like the Lone Star. I don't know. I didn't come up with that. That's just what people call them. A ring structure like that is a common spot for those to occur. Another one is on a carbon double bond oxygen. Be careful not to do something like that, which has the same problem. We've got 5 bonds to that carbon. For electron domains, the oxygen plus 3 carbons, but there's a double bond there. So the double bonds are sort of often a culprit for accidentally giving carbon 5 bonds. Okay. I mentioned this briefly, but always and forever include all formal charges. So from our little oxygen example that we talked about, that's okay. We have an oxygen with a negative charge, and it's okay for an oxygen with 1 bond have a negative charge. You'll notice I haven't drawn in lone pairs, and that's okay. But particularly for things that are charged, it's not bad practice to draw them in. And also, if you're trying to figure out, okay, does this have a formal charge or not? Of course, eventually you'll get it, so you just look at it and know. But if you're not sure, you can say, all right, well, oxygen should have 6 valence electrons because it's in group 6. Here it's got 1, 2, 3, 4, 5, 6 from the lone pairs, 7 from that bond. So it's got an extra electron. Electrons are negative, so it has a negative formal charge. We're going to talk about carbons with formal charges next, but I'll give you a sneak peek. Sometimes you'll see something like that. So a carbon with a lone pair, that requires a negative charge. And in fact, this is, I don't know, doesn't really make sense for me to redraw that with a hydrogen because that carbon doesn't have any hydrogens. So we'll get to that actually right now. So heteroatoms with formal charges are comparatively easier because you have to draw out the heteroatom. And more importantly, you have to draw out any hydrogens attached to the heteroatom. So that oxygen up there, we don't have a hydrogen drawn to it. And so we know for a fact that there's no hydrogen attached to it. But with carbon, we usually don't draw out the hydrogens. And so now I've just gotten you into the practice of carbon always has to have 4 bonds. Well, guess what? If it's got a formal charge, it has 3 bonds. Okay. So carbon has a formal charge if it has 3 bonds. And the opposite, not the opposite, but the reverse logical statement is true. If a carbon only has 3 bonds, it has a formal charge. So if we have just this skeletal structure, okay? The carbon in the middle is drawn with only 3 bonds, but it's only 3 bonds to other carbon atoms. Ugh, sorry. So that is actually that. Okay, there's one hydrogen there. And so here carbon actually has 4 bonds. And in all of these cases, we're talking about the carbon in the middle here. So that middle carbon has no formal charge. So it's got 4 bonds. 1 bond to hydrogen, but 4 bonds. If the carbon has three bonds with a lone pair, it's negatively charged. And we call that a carbanion. So an anion is something that's negatively charged. It's a carbon, so it's a carbanion. Some examples of those would be, right? So this here, which I already showed you, that has no hydrogens on the central carbon. Again, just the central carbon here. So this carbanion, how many hydrogens are on that carbon? 1. So this is where people often get confused, because if you ignore the lone pair in the charge, that looks like it should have 2 hydrogens on it. Another way you could think about this is ideally carbon should have 4 bonds. And so we've got a bond to carbon, a bond to carbon, a bond to hydrogen, which I haven't drawn. And then that lone pair is sort of that 4th bond, but it's not bonding to anything. It's still stuck on the carbon. So in this case, the carbon still has a full octet of electrons. It's just missing that last bond. And so it gets a negative charge because those electrons are held close to it. Okay, and then finally, if we have it on the end, this is going to have 2 hydrogens on that carbon. So another way to draw, okay. So there's that one. Drawn with its hydrogen, and then the one with 2 hydrogens. So when we draw out the hydrogens, now we can see the 3 bonds in each case. 3 bonds, all of them to carbon. 2 bonds to carbon and 1 to hydrogen. 1 bond to carbon and 2 to hydrogens. All 3 bonds, all have a lone pair, all are negative, have a negative formal charge. Fortunately, you really only have to remember one set of these because it's actually the same thing for a positively charged carbon. And if an anion is negative, a cation is positive. So it's a carbocation, not a carbocation. So we can literally just redraw this without the lone pairs and with a positive charge instead, and it still holds. I will draw the hydrogens explicitly the first time here. Same structures, just without the lone pair. And that's the difference between a carbanion and a carbocation. These are going to come back in a little bit. By a little bit, I mean March, early March. But we aren't going to be too concerned with them in the immediate present. Okay, so these are sort of a thing you should file away for later kind of concept. Okay, so we've talked about lone pairs on carbon. On carbon, the lone pairs, I mean, they should be drawn, but you don't have to draw the lone pairs on the carbon. You could just draw a carbon with a negative charge, and that implies the same thing. It's not incorrect. Of course, I would highly recommend you draw the lone pair because that tends to decrease confusion, but you can do that as well. So that's for carbon. Let's talk about lone pairs on heteroatoms. And heteroatoms are everything except what? Carbon and hydrogen. So lone pairs on heteroatoms are optional. Now, of course, when you're drawing them, when you're drawing structures, I recommend that you draw the lone pairs. But just as equally, I'm going to give you structures that usually don't have the lone pairs on them. Mostly because it's tedious to do on the computer versus not to draw the lone pairs. But also because in the wild, you'll see them drawn like that. Also, just the dots, a bunch of dots, it's easy to not see those or something. So they're optional, but you definitely need to be able to fill them in, because when we start drawing chemical mechanisms, very often you're going to need a lone pair on a heteroatom to do some work. I know that didn't really mean anything, but they tend to be the ones that do the work in a lot of chemical reactions. So for this, review the formal charge cheat sheet again. For this is going to be important. So here's some examples. Sorry, that was ugly. Here's some examples of compounds with heteroatoms on them, in them. And each of these heteroatoms has one or more lone pairs. And at some eventually, you'll need to be able to fill these in, ideally without looking at the sheet. But let's do them, I guess. What about the oxygen? How many lone pairs should that have? 2. Nitrogen? 1. Fluorine? 3. Honestly, the halogen lone pairs are probably the least important, even though there's the most of them. And then sulfur. 2. Sulfur is just fat oxygen. And so in almost all cases, you can replace sulfur with oxygen if the big element scares you a little bit, which I fully understand. And it should look fine replaced with oxygen. Like that. Okay. So we talked about first we talked about condensed structures, talked about skeletal structures. Oftentimes we kind of merge them together a little bit, as in we draw like 80% skeletal and then a little bit of condensed where we find it's convenient. Okay. It sounds ridiculous, but I think it'll make sense in a second here. So let's take the skeletal structure of this compound, methyl butyrate. Probably smells nice. Usually these compounds tend to smell nice. Anyway, so we've got this is a full skeletal structure. But many times, I don't know about you, but this line over here, you might take that as a negative charge. I mean, I know I told you to circle your charges, but maybe you think it's a negative charge. Maybe it looks like a straight line or something like that. And so sometimes to get around that, we will draw kind of the any ambiguous parts as condensed structures. So here, this bit, skeletal, and that part is condensed. If you want, we could take it further, and this is something that a lot of organic chemists will argue that you should always do, but the ends of lines, that's a carbon with 3 hydrogens on it, always and forever. But who says you weren't like drawing a molecule, but wait a minute, there's some other stuff over here you just forgot to draw it. That's totally possible. And so some people, not including myself, because I'm lazy, but not including myself, will argue that you should draw out that carbon explicitly. So I'm going to go, well, I have to draw the same thing anyway. So OCH3. And what you can also do on the left side of that molecule is put in the CH3. Now, don't just write CH3 because the bond right there, that leftmost bond, is a carbon-carbon bond. So there's a carbon right there, but this is not complete. If we draw out a carbon explicitly like this, we have to draw out the hydrogens. And that's usually just done with an H3. So any group on the left, and this is drawn out like a skeletal structure, CH, with the letters CH3, but those have to be backwards. To show that the connectivity is from carbon to carbon, and we don't have like a hydrogen, like 3 hydrogens bound to, kind of gets to be a big mess. So make sure that you're showing the bonds to the atoms that you actually mean. Another example would be OH groups, alcohols. So we might have a CH3 over on this side, but if we have an OH group at the end of that bond that I've just drawn, rather than being OH, it has to be HO. To show that that bond is to the oxygen and that the hydrogen is hanging off the end. Okay, so go ahead and take a minute or two. Draw me a skeletal structure of this compound. Make sure you have all the required items. And if there's optional items, they're optional. You can draw them or leave them off. All right. If you need to make an ugly draft drawing before a nice, pretty looking drawing, that is totally okay. Okay, so there's a couple of right answers. If you didn't put one of these, that's okay. That doesn't mean your answer is wrong. But the requirements are, well, I said draw a skeletal structure. So you probably shouldn't have drawn out any of the carbons explicitly, but if you did, that's not illegal, I guess. The oxygen must have the positive charge, but the lone pair is not necessarily required. You must draw the hydrogen attached to the oxygen. You can draw it with a bond or without a bond. That's okay too. Now you'll notice this is the one I would probably draw, but also I've been doing this for too long probably. You'll notice I've drawn out this hydrogen explicitly, which I never told you to do. And that's okay. That's because this hydrogen ends up being important for reactivity a little bit later down the line. So something like this is also, anyway. So those are a couple correct answers for this. How do we feel about that? Okay. Yes.
On the left one.
Yes.
To start like the carbons, like on your other skeletons, you start going up and then down. So you go to start from there.
You can go whichever direction you want. You can go sideways, backways, upways, all the ways that Willy Wonka says his elevator goes. Yeah, so it doesn't matter. When you're drawing sort of long and skinny things like this, I don't know, I just instinctively start by going up. But you can go any direction. So you could, let's see. We could do that. That's fine. Or any rotation or orientation of any of these, in fact. Okay. So now we've introduced, so organic chemistry is kind of like a language, if you haven't noticed already. You can make all sorts of little analogies to how it works, but we've sort of learned how to write letters and to draw letters and write words, basically, in this language. Functional groups is sort of like the definitions of the words, if you like. But basically, what a functional group is, it's a part of a molecule that has predictable functionality, hence the name functional group, predictable reactivity, properties, et cetera, et cetera. Now, that's really vague, and it's vague on purpose because really any part of a molecule that you want to talk about, you could call that a functional group. We're going to see that there's a relatively small, I don't want to say relatively small because I'll get your hopes up, but a relatively small list of really common small functional groups that come up really often. So the reason we've done all this crap with drawing skeletal structures is because it gets the clutter out of the way and allows us to see those functional groups really fast when we look at a molecule. So these important clusters of of atoms. Could be just one atom, technically. So an example, this is our first reaction, by the way. We're finally doing some chemistry, even though it's not actually one that you need to know quite yet. So if we have this molecule, what's the only interesting thing about this molecule? The double bond. So I guess you could say functional groups are just the interesting parts of the molecule. Okay, so we have that double bond, that is a functional group. Specifically, it's called an alkene, but we'll get there. So let's say that we want to do a reaction, and I'm going to use H2, hydrogen gas, and actually a precious metal, palladium, as a catalyst. We'll learn this reaction in late March. And the product of that reaction is this. So if I were to draw the Lewis structure of this, you would have to go through and like look at every single atom and every single bond trying to figure out what the hell just happened. But here, instantly you see, oh, the double bond's gone. That's the only thing that's happened here. This is the power of skeletal structures. So in this case, often we turn one functional group into another. You could kind of argue that here we've just gotten rid of a functional group, but that counts just the same. Okay, so the skeletal structures help us see functional groups. But what if we have an even bigger molecule than this? What if we have a protein that is how many carbon? I don't even know how many carbons are in a protein. Lots of carbons in proteins, DNA, large, especially biomolecules, but some other molecules too, like polymers. And at that point, even skeletal structures are not adequate to abbreviate a molecule. And so in that case, and even in smaller cases too, we're going to use what we call an R group. And that's a variable atom or atoms. Often it's many atoms. That's attached to a core structure. And generally, if functional groups are the interesting parts of a molecule, the R groups are the boring parts that we don't care about. And we just abbreviate it to R and call it a day. There's certainly some dangers in doing that, because what if your R group is actually doing some reaction and you're ignoring it, but it's a problem? That happens more often than I would like to admit, but it is useful. So in our reaction, we have the functional group, the double bond on the right-hand side. I would consider that to be the interesting or the reactive part of the molecule. But there's this branch over here on the left that is not doing anything. So, sorry. I'll just go up here. There we go. So this little group of 3 carbons is unaffected in the reaction. With a small molecule like this, it's not a big deal to draw it out. But what if it wasn't a small molecule? What if this 3 carbon group was really big? In particular, this one is called an isopropyl group. Doesn't matter quite, well, actually, it's going to matter in like 5 minutes. But for these purposes, it doesn't matter because we're just going to abbreviate that to R. So R. And so R just ends up looking like an element. Like it's a halogen or something. But it's not. It's something very specific that we don't care about. In this case, an isopropyl group. And so if we wanted to be very specific, if we were just showing that, I almost went to cover up something on the iPad so you couldn't see it. It didn't work. Sorry. If we didn't have this information over here, if we just had this structure, I mean, without this information, that tells you something about this part of the molecule, but then it just says there's something else over there that we don't care about. Many times, okay, you need to actually be specific so we know what chemical we're dealing with. And people will sometimes just write R equals whatever. The good thing about that is if you've got a bazillion variations of one molecule, you can use this notation to make it efficient. So the key here is that using an R group puts the focus on your reactive functional group or functional groups. So functional groups are important. I don't want to say R groups are not important, but they're less relevant to the current situation. If you're curious, R stands for radical. That's where the R comes from. Okay. So if you go on Blackboard, which I would recommend you do if you have your phone, go ahead and do that because we're going to use this information in a moment. If you go on Blackboard, you should find on the front page a table of functional groups. So this is the small list that I told you about of common functional groups that you will see in organic chemistry. So let me tell you a little bit about what the diagrams here are talking about. You'll notice that all of them have at least one R group. Some of them, like this alkene or olefin, have multiple. But in a larger molecule, if we're looking at one functional group and we're only concerned with that functional group, right, we can get rid of the whole rest of the molecule. R means radical, but you can also think of it as being the rest of the molecule, R for rest of the molecule. So if we have some sort of large molecule, R, and attached to it is this pattern here, a carbon with one hydrogen, with two branches of single carbons with three hydrogens, that is an isopropyl group. Okay? So, for example. Okay, let's see here. I should divide things a little bit like that. And then this should also get its own. Please make it. Oh, okay. We'll do a hand-drawn square then. Okay. So there's actually two sort of big subdivisions here. So this first one is the alkanes. So alkanes are just bunches of sp3 carbons that don't really have any interesting functional groups attached to them. So I talked about in our example from above that the alkene was the functional group. And to some extent, you could say that these alkanes that are just carbons with hydrogens attached are functional groups. They're kind of the lack of a functional group. And so I just want you to be able to see these various different kinds of alkane substituents. That's another name for functional groups. So these are some various collections of alkanes that you might see. So they're like the not functional groups. If we continue down that side of the page, okay, now we see that a lot of these contain multiple bonds or heteroatoms, because that's kind of how you get something to not be, So double and triple bonds have their own names. Alkenes are carbon-carbon double bonds. Alkynes are carbon-carbon triple bonds. You've probably seen these six-membered rings with alternating single and double bonds. That's called a phenyl group if it's by itself, or an arene if it's attached to other things. The class in general is called aromatic. If you have a halogen attached to your molecule, it's extremely vague, of course, but it's quite common. It's called an alkyl halide or a haloalkane. Alcohols, I think we know what alcohols are. It's an OH group. Ethers, peroxides, and epoxides are all different versions of oxygen in the middle of carbon atoms. So hydrogen peroxide is where R is hydrogen, for example. Amines are nitrogen-based, so nitrogen with three bonds. You'll notice I have primary, secondary amines, and then at the top of the next bit, tertiary and quaternary. We'll talk about those different levels in a little bit. Anything with thio in it has to do with sulfur. We won't talk about those too much. Then the next big group is sort of all of these are types of not carbonyl, but carbonyl compounds where we have a carbon-oxygen double bond. And these are all over the place, hence why there's a large range of different ones. So you'll notice that all of these, what is it, 9 or so, have a carbon in the middle with an oxygen double bonded to it. Generally, we write it going upwards, but again, it doesn't matter which direction you write it. So aldehydes and ketones, carboxylic acid, ester, acid anhydride, and the list goes on, basically. You'll also notice, and this is something that should also be mentioned with the alkanes, is there's some abbreviations that are often used. So in short, if we have an aldehyde, you can draw the structure out like this. We have our R group, whatever it happens to be, attached to a carbon. That carbon's attached to double bonded to an oxygen and a hydrogen as well. Or, and I don't necessarily recommend you do this, but you need to be able to identify it. You could just write CHO, and that's sort of the condensed structure way to write some of these carbonyl compounds on the right. But then on the left at the top, you'll notice that some of these, actually in this case, all of these alkanes have specific abbreviations. And for these, like ME for methyl, we call those pseudo element symbols because they look like elements. Me is not an element. It just means methyl, CH3. ET, ethyl, PR for propyl. And then you'll notice that there's two different kinds of propyl groups. The regular N for normal propyl, which is just a straight chain. And then isopropyl, which still has three carbons, 1, 2, 3, but they're in this other configuration. So sort of the attachment point is in the middle. And then there's a variety of different butyl groups with the symbol Bu, in butyl being a straight chain of 4 carbons, and then these various other arrangements of 4 carbons. There's pentyl and hexyl. There's larger versions, but they tend to not come up quite as often. Okay, so there's your functional group chart. Those you'll need to know pretty well before the exam. But I will probably end up getting rid of maybe some of the butyl ones down here, and maybe some of the more advanced carbonyl groups, like the ones at the bottom, that we don't see until organic 2. So I'll keep you updated on that. Okay, so keep that chart up on your screen if possible. It's the 20th. Oh my God, it's the 20th of January already. Okay, so let's get some practice identifying these in a molecule, because you can look at that chart, you can memorize that chart all day if you want. But I'm going to get what's going to happen on the exam is I'm going to do this. I'm going to give you a molecule. No, I don't want to do that. I'm going to give you a molecule and say, okay, point out to me 3 or 4 or however many different functional groups and label, give me their names, that sort of thing. So this is not a real molecule. At least I don't think this is a real molecule. I just pulled it out of my ass. But go ahead, and there's a good variety of different functional groups that are in here. So see if you can go and name as many as you can. I'll start with an easy one. Me is a methyl group. Any volunteers? Okay, so Br, what kind of element is bromine? It's a halogen. So we have some part of the molecule attached to a halogen. So that is an alkyl halide or a haloalkane. What about the double bond that has a specific name? Yeah, alkene. What about the pH? That one gives you half the answer almost, but yeah, phenyl. Okay, so there's two oxygens. What about that oxygen? So it's got two single bonds to different carbon atoms. So both of these carbon atoms, you could call those R, because it doesn't really matter what else is attached to them. So what functional group has R attached to oxygen attached to another R? Yep, ether. And yes, the ether that you soak with a rag and put over, it's the same kind of ether. Okay, maybe the trickiest one is this guy with a carbon-oxygen double bond. So the general name for all of the different CO double bond compounds is carbonyl. But in this case, we specifically have a carbonyl that has two R groups attached to it, two carbons. And so what is that? Yeah, it's a ketone. Also, one thing I should point out is that that's also a methyl group. I just didn't write Me. All right, so Me or CH3 or an end of, well, let me put, I can put another group here. There we go. That's also a methyl group. So 3 different ways to write a methyl group, okay? All right, I will see you on Thursday.